And so, you know, we eliminated, we isolated the term with the x, right? And we got a simple equation like cosine is equal to root 3 over 2. And then we asked ourselves, for what angle is cosine root 3 over 2? We found that it was pi over 6, but we had to look in different quadrants where cosine is positive to get our two values. And then, why did we put the 2 pi n or the 2n pi? What was the reason for that?
It's like every 2 pi.
Because it repeats, right? That y value of root 3 over 2 repeats every 2 pi. Okay, we're going to do another one now. So again, the process is the same every single time. Isolate the function with the cosine and then find the value of the angle. Yeah.
This is a dumb question, but is 2n pi, like, are those you writing the same? Never mind. Doesn't matter whether you do 2n pi or 2 pi n, same thing.
Correct. My preferred is 2 pi n. I don't know why I wrote 2n pi, but then I did write both so you guys see that it's the same. Okay, so here I have 3 tangent squared x minus 4 is equal to negative 3. So where are we going to start with? Yeah.
Getting tangent all by itself.
Getting tangent all by itself? And isolate the tangent. And so what is the first step I need to take to do that? Plus 4 to both sides. So now I have 3 tangent squared x is equal to 1. Now I need to divide both sides by 3. So tangent squared x is equal to 1 over 3. Now, take a square root, take a square root. So, tangent of x is what?
1 over root 1 over 3.
Okay. There we go. It's 1 over root 3, but plus or minus 1 over root 3. Okay? Now, is 1 over root 3 a familiar value?
Yeah.
That is a familiar value. So now, I need to figure out the angle for which tangent is 1 over 3. Okay? 1 over root 3. Question?
Why is it root 3 and not?
So it is root 1 over root 3. So when I do that, I get root 1 over root 3. But root 1 is just 1 over root 3. Okay? Now I need to figure out where tangent is 1 over root 3, right? So for what angle? For these, we have to look at our triangles. So remember we have 3 triangles, right? I have a 30, 60, 90. So I have the 30 degree. I have the 60 degree. And then I've got the 45 degree. Right? So for the 30 degree, this is what it looks like. For the 60 degree, this is what it looks like. And then this is what it looks like for the 45. Okay, so now if I want tangent to be 1 over root 3, that's vertical over horizontal. Vertical over horizontal. Am I going to get a root 3 with the 45 degree triangle? No. So it's got to be 1 over one of these. If it's vertical over horizontal, right, I want the root 3 to end up on the bottom, right? So I want the one where the root 3 is going to be on the bottom. Okay, Noah?
Oh, can I?
Yeah, tell me.
30.
30 degrees, I have 1/2 over root 3 over 2. That's the one that gives you 1 over root 3 for tangent. So 30 degrees means x is pi over 6, right? But now, I'm going to write that like further down here because look, there is something else here. When I have tangent is 1 over plus or minus 1 over root 3, that tells me 2 things. tangent of x is 1 over root 3, and tangent of x is negative 1 over root 3. Okay? Plus or minus means tangent of x is equal to positive 1 over root 3 and negative 1 over root 3. So let's go in our quadrants here. Okay, so I said x equals pi over 6, right? That's here. Now, so take a look at this one. This tells me tangent is positive 1 over root 3. Is that right? Okay, in which two quadrants is tangent positive? In the first and the third. Okay, so what's the corresponding to pi over 6 in this one? What angle is that?
7.
7 pi over 6. So here, the angles are x equals pi over 6, x equals 7 pi over 6. Now look at this. This tells me tangent is negative 1 over root 3. So now I have to look for the pi over 6 equivalents in the quadrants where tangent is negative. That's in quadrant 3, tangent is negative, and in quadrant 4, tangent is negative, right? So what are my equivalents in those quadrants? 5 pi over 6 and 11 pi over 6. Whew. Okay, now, take a look. I need to do plus 2n pi for these, okay? So my answer is going to be x equals pi over 6 plus 2 pi n, 7 pi over 6 plus 2 pi n, 5 pi over 6 plus 2 pi n,
Bless you.
11 pi over 6 plus 2 pi n. Okay, I know. So how did we end up with 2 for the first problem and 4 for the second problem?
Because it was plus or minus.
Right, it was plus or minus, so there are 2 quadrants where tangent is positive, 2 quadrants where tangent is negative, okay? But you're not going to get more than 4 though, because there are only 4 quadrants. I mean, for each one like this. Okay, how does that feel? But I find students have an easier time with this to start than like 5.1, you know, like the other simplifying stuff in 5.1. Yeah.
I just don't get how. Oh, wait, never mind.
Awesome. Okay, take a look at this one. Now look at the instructions here. It says find the solution of the equations over the interval 0 to 2 pi. Okay, when it tells you 0 to 2 pi, that means we're only going around the circle once. That means, this part means you don't need the plus 2 pi n. Okay? Questions? That's what that means. So because we're not going to do plus 2 pi, because we're only going to remain in that one circle. All right, so let's take a look at this. All right, in here, I have 2 sine x cosine x equals root 3 sine x. All right, so I'm going to take a poll here. What would you say the first step should be? Yeah.
Divide by 2 cosine.
Or by
Or
sine?
I mean by sine.
Okay, this is 100% of the time the first instinct for every single person who sees this for the first time, right? And it's a very, very strong urge to just divide, divide, divide. Now I'm going to tell you, you have to resist that urge to divide. It's very, very natural that that's what you want to do. But when you divide by sign, you know what you do? You get rid of the sign, you eliminate half the problem, and you eliminate half of the solutions. So instead, what we're going to do is we're going to take everything to the same side and factor. Okay? So I'm going to subtract root 3 sine x from both sides. So I'm going to get 2 sine x, 2 sine x cosine x minus root 3 sine x equal to 0. Okay. Now I'm going to factor out a sine x. And we learned how to do that in section 1, or we reminded ourselves how to do it. When I factor out a sine x, I get 2 cosine x minus root 3. Does that make sense?
Yes.
Okay.
Why do you have to factor this out?
In order to be able to solve it. Because now, look at what we're going to be able to do now. Now I have sine x times this parenthesis equals to 0. When you have two things that are being multiplied and they equal to 0, you can set each one to 0 separately. So now I can say sine x is equal to 0, and this part is equal to 0. Does this make sense?
Yeah.
Now let's solve. Okay, where is sine x equal to 0? All right, if you go on the triangles, are you going to get sine x equals 0 from here? No, we need the unit circle for that, right? Remember our good old unit circle? This is a quadrantal angle. So here I have x is 1, y is 0, 0, 1, 0, negative 1. Okay? So where is sine of x 0? At 0 and pi.
What about 2 pi?
Okay, so let's see. So here, x is 0, x is 2 pi. Okay, you see here, when it says 0 to 2 pi like this, if it's got like a parenthesis here, that means you don't have to include the 2 pi.
Oh.
Now, if you put the 2 pi, am I going to take points off? No, I'm not. So it's going to be 0, pi, 2 pi, and so on. Okay? Now, let's solve this one. I'm going to add root 3, so I get 2 cosine x equals root 3. Divide by 2. So now I have cosine x equal to root 3 over 2. And where is cosine equal to root 3 over 2? The other one. The 30 degrees, which is pi over 6. So x is pi over 6, but now I got to get 2 quadrants, remember? So pi over 6 and, oh, look at you guys, 11 pi over 6. So the answers are this and this. Many, many answers for this one. Okay? Yeah. I was just checking. Okay. We're cool? Okay. Now, so again here, I've put a representative problem of each type that you might encounter. Okay, here's another one here. I have 2 sine squared x plus sine x minus 1. Okay, this is another one where we have to factor. But now, is there a term that we could just factor out like we did with the sine? It's not possible for this one. We have to factor this a different way. So let's remind ourselves how we factored. If you have 2x squared plus x minus 1 equals 0. Do you remember how to factor problems like that? Right, where when you have like 2x plus something, x minus something. Right, so let's look at the form here. I have a variable squared, and then the variable to the power of 1, then a term without the variable. So power of 2, power of 1, no variable. here, it's the same pattern, but instead of the x's, I have the signs. Instead of x squared, I have sine squared. Instead of x, I have sine. And then, no function. So the function squared, the function to the 1, nothing there. So they factor in the same pattern. All right, so what's your preferred method of factoring this quadratic equation here? Do you multiply? Have you learned the system where you multiply the 2 to this? Yeah? All right, so let's do it that way. Let's multiply the 2 to the 1. How does that work? X squared plus x minus 2 equal to 0. Right? And now I'm going to factor x plus 2 minus 1. But now, since I took out a 2, I got to put the 2 back. Okay? You remember how here I multiplied the 2 into here?
Then that would be 4x squared.
Okay, but now I look at each parenthesis. If there is one that needs to be simplified, then I simplify it. So I look at this parenthesis here. I can divide these by 2. So I get x plus 1. But I can't simplify the second one, so it's just 2x minus 1. This is one way of factoring. If your preferred method of factoring is like guess and check, then do guess and check. The point here, I'm not teaching you how to factor. I'm just reminding you how we factor, and now we're going to use that for that same process there. So, you see how we got x plus 1 and 2x minus 1? That sign equation factors in the same way, but instead of x's, I have signs. So the way I factor this one is sine x plus 1, 2 sine x minus 1. Okay? All right. Are we all okay with how we factored this? Okay, now, look at this. I have one thing times another thing.
Does it matter where the plus 1 and the plus minus is?
Yes. The minus 1 has to be with the 2, and the plus 1 has to be with this one, because when you now go backwards and you FOIL, it has to give you that top equation back. So when you FOIL and you do like negative sine x plus 2 sine x, you should get this positive sine x back.
Why in this one you have 2x plus 2 and this one you have half plus 2?
Because she multiplied.
I divided by 2 here to simplify the 2's, and I only got x plus 1. Yeah.
Oh, okay.
I just went to the bottom one immediately. Okay. So now look, here is the most important thing you'll learn in this lesson. It's something multiplied by something equal to 0. Is that right? In the top here, I had sine x times this parenthesis equal to 0. In both of the cases, I have one thing multiplied by another thing equals to 0. This is the only time that you can say that individual terms are equal to 0. The most common mistake I see here, whether it's in Trig or Algebra 2 or Algebra 2 Honors, Pre-Calc Honors, across the board, is if like something looks like this, sine x plus 1, 2 sine x minus 1 equals, let's say, 1, right? Then they say, okay, this is equal to 1, this is equal to 1. You can't do that. The property which lets you now say each one of these is equal to 0, right, individually, you know what that property is called? It's called the zero product property. It means when you multiply them, their product must be 0. So only when this is equal to 0 can you now say each individual parenthesis can be set equal to 0. I can't stress this enough. Please don't lose points over this, okay? So for you to be able to factor in the first place, Everything has to move to the left side. Everything has to equal 0, then you factor. Okay, now let's move on here. So here I'm going to subtract 1. Sine of x equals to -1. Here I'm going to add 1. 2 sine x is 1. Divide by 2, divide by 2. Sine x is 1/2. How does this, is everybody okay with this? Any controversy here? All right, let's see. The first one, where is sine x equal to -1? Can I get that from the triangles or do I need to go to the quadrantal angles? Quadrantal angles. So where is sine x equal to -1? At here. Sine is the y value, right? So it's at 3 pi over 2. So x is 3 pi over 2. Next, where is sine equal to 1/2? Pi over 6 again, but now I need 2 quadrants. So sine is positive here, and in the second quadrant, 5 pi over 6.
Is it ever gonna be 5
You're waiting for the pi over 3, huh? I don't know why these are all coming out pi over 6. I need to revise my notes for next year. It is, yes, pi over 3 and pi over 4 are just as special as pi over 6. Yeah, we don't discriminate here, right? Okay. All right, so let's...
Do you not add the 2 pi into those?
No, because this one too, it said from 0 to 2 pi. Yeah, that goes for all of them. Okay. Okay, what's the problem here? What's the problem here?
You have to get 0.
You have to
move cosine to the other side.
Okay, so let's move the cosine to the other side. Sine squared x minus sine x plus 1 minus cosine squared x is equal to 0. But now there's another problem. There is another problem. Cosine. That cosine, man, it messes everything up.
Yeah.
It's all in terms of sine, and then there's a cosine. Remember what we said before? It's never a good idea to just have a blended soup of all these different trig functions. We have to make it uniform in terms of one trig function. So, how to get cosine squared to look like a sine squared?
You do 1 minus cosine squared. Sorry.
Is there a Pythagorean identity?
Yeah.
Sine squared x plus cosine squared x is equal to 1. Okay? Sine squared x plus cosine squared x is equal to 1. So, what's cosine? Okay, so there are 2 ways we could do this, but what's cosine squared equal to? 1 minus sine squared x. All right, so let's do that. Sine squared x minus sine x. Okay, now look.
So let's say you got cosine.
Wait a minute. I think
You just do 1 minus what you got and then sine equals cosine.
Huh?
Why didn't you do 1 minus cosine squared equals 1?
Why wouldn't it just be sine squared x?
Okay, so there are 2 ways of doing this. One thing is, you can just substitute for the cosine squared x. And then another thing is, if you realize that 1 minus cosine squared x is sine squared x, you can do that too. Okay? So this is just positive sine squared x. I love that you guys saw that like that. Good. Oh, what? Now what? What do we have? Sine squared x plus another sine squared x is how many sine squared x's together? 2 sine squared x.
No.
1 sine squared x plus another.
Up there is 1 minus sine squared x. So why would it be?
Okay, so we said there were two ways to do it. That was one way, and then another way was if I move the cosine squared x to the other side, I get sine squared x is 1 minus cosine squared x, right? Right, so if I subtract cosine, sine squared is 1 minus cosine squared x. And then in the equation, since I already have 1 minus cosine squared x, I can just make that substitution. So now I have 2 sine squared x minus sine x equal to 0. Here, I'm going to factor out a sine. It's going to be pi over 6 again. So I factor out a sine, and I get 2 sine x minus 1 equal to 0. Hey, do I have one thing times another thing equal to 0?
Yeah.
Yep, now I could use that zero product property. Set them each equal to 0. Don't you guys love math?
Mm-hmm.
Okay, so this one is already solved for me. Sine x equals 0. Here, add 1, add 1. 2 sine x equals 1. Divide by 2. Divide by 2. Sine x is 1/2. Okay, so sine x equals 0, right? For the first one, I have to go to my quadrantal angles. And sine x equals 0 at the 0, at the pi, at the 2 pi, right? So x equals 0, pi, 2 pi. And sine x equals 1/2, it's becoming very boring and predictable now. At the pi over 6's. And which other quadrant?
Pi over 6.
Yep. Okay. Okay, so the homework, it's not what it said over there. It's page 331, numbers 139, 11, 15, 23. And for now, I'm going to skip D in the notes. But none of this require D. All of these are based on what we just did right now. Okay? So